Hi, my name is Matt Reed. I'm here today to show you a little bit about this robot arm that I designed. We designed this to take to pre-cal classes, high school classes, to discuss a little bit about what they've learned and how they can use the math that they've learned in robotics. So we have this basic two-joint design. On each joint, you can see around the wheel, you've got all of your different theta 1 values. Now, theta 1, it measures, so if we have our x, going horizontally and our y going vertically, it's going to measure the angle between our x-axis and the center of my my first link. So we can set that value in this viewing window. We can set it to anywhere, any one of these degrees. Now, once we set that, each robot arm we're going to have two limiting toothpicks. What those do is they limit my rotation. So right now I've got this set to limit between, let's see, 0 degrees and 75 degrees. In order to do that, so if I add 30 degrees to 75, I get to 105. So if I want to limit this theta 1 value to 75, I actually put my toothpick at 105 degrees. So I just add 30 degrees to where I want to set the limit, and that's where I put my toothpick. So here I've got it set at 0, so I actually had to go to the 330 degree mark. Now theta 1 is always limited. We always have this toothpick here, so it's always limited to 315 to 225. These toothpicks down here are not removable. They're always there. That is simply for the robot to be realistic. Most robots aren't going to have a full 360 degrees of motion. Even my theta 2 value, no matter what, I can't get 360 degrees, right? It's gonna hit other parts of the robot. So then we've got all of these holes on here. So what do all these mean? These smaller holes are my toothpick holes. Those are going to either limit my rotation, or there's a toothpick hole in the center here. So let's say I want to lock theta 1 into 15 degrees. So this toothpick, I don't know if you can see it there, actually goes all the way through. So once I set that, it's locked in. I can't move this first joint anymore. So whenever you tape this down to your desk, if you want to lock that in just to make sure that there's no movement so that you can get more accurate measurements, that's what that is designed for. Now here, what we can do is we can actually use these holes. R1 is fixed at 15 centimeters, but we can use these holes. Each measurement is listed there. So we can use those holes to actually draw out shapes inside our workspace, which is all of the places that the robot can put its end effector. It's going to be a volume that is swept out by the end effector as the robot rotates through all of its motions. And then, of course, R2, we have all these different values. So we actually get to pick the length of our second link. So as theta 1 is set, what we do is we want to, if I set it at 15 degrees, I want to make this little arrow point directly at the 15 degree line. If I want to set theta 2 to whatever, I want to make sure that this arrow is pointing directly. Now, the toothpick holes are also really helpful for that. So I've got this almost to 60, but the toothpick won't go all the way through, so I know it's not quite. So as I move it back, I can feel the toothpick go through. It locks. I'm actually set at 60 degrees. So a little bit about the design and the way these are assembled. The designs are uploaded on University of Houston's Robotics Thingiverse. So with that, you've got the AutoCAD files. If you have access to a laser cutter, you can actually cut out one of these arms. Now, what it's going to do is you're going to cut out these 3 pieces. Now the 3 pieces, the way that we have them assembled, we've got a little washer with a rivet that goes all the way through. Now we added the washer because what was happening was the rivet was pulling through and it was stretching out the wood at the holes, and it was actually shifting this to where it was a little off center. So once we added that washer, now the rivet is pulling towards the washer, stopping at the washer, and that's what's locking it into place. It's a much stronger hold. I would definitely recommend, if you're going to use rivets to hold these robot arms together, use the washers. It's going to help out a lot. It also, if you add a little bit of graphite, you can just take a pencil and mark up the back, put a lot of pencil lead on there. It's going to make these move a lot smoother, which you're going to see later in the video why we want those to move smooth. If you lock this down and are trying to use your pencil to draw out the workspace, your pencil's going to break and break and break and break, which you can see this one isn't that stiff, but it's still fairly stiff. Now obviously the more you move these, they're going to loosen up. So that's the basic overview. I named it RR3 just because it's 2 rotational joints. We've got a base link, and R1 and R2, which is our normal link. So it's a 2-joint, 3-link robot. Okay, so the first thing we can do with our robot arm is set up the origins of our 2 coordinate planes. So what we're gonna do is we're gonna set theta 1 to 30 degrees, and so this is gonna be origin 0, our plane of reference, and this is gonna be origin 1. So in order to set that up, first you set theta 1 to 0 degrees and make a mark on that circle. Set theta 1 to 90 degrees, make another mark, and then you're going to set theta 1 to 180 degrees and make another mark. And then you've already got this hole to make this mark in the center. So now that I've got my 4 dots, when we get done, we can remove the robot arm, connect the dots. Where those lines cross is going to give us our first origin. So now we're going to set theta 1 at 30 degrees. So we're going to lock it in with our toothpick. I can't move theta 1 now. And we do the same thing. We move theta 2 to 0 degrees. Make our mark. Move theta 2 to 270 degrees. Make our mark. Move it to 90 degrees. Make our mark. And then we're going to make another mark there. So now I've got these 4 points, and so when we connect that, we're going to see this XY coordinate system. So obviously we can see that our second frame is going to be just simply rotated by 30 degrees. That's given by theta 1 at a distance of 15 centimeters, which is given on our robot arm. So now the main point of this robot arm, we're going to set, we've already set theta 1 to 30 degrees, we're going to set theta 2 to 105 degrees. Now if you do not have a calculator, if you use 0, 30, 45, 60, 90 degrees, the angles that we're so familiar with from the unit circle, if we use those, we don't need a calculator. Because we already have those, the cosine of those angles. However, I'm going to set it to 105 so that we can use our calculator to calculate our distance. So I'm going to lock that in, and I'm going to let R2 be 11.25 centimeters. So, as you can see on the screen, we've got our law of cosines, and that's what I'm going to be plugging into my calculator. So, if I plug in so we have an equation for d squared, okay, the distance from the center of our first joint to the end of our end effector. We have the equation for d squared. So all I do is plug in the square root I'm going to do the square root of R1 squared. R1 is fixed at 15 centimeters. So I do R1 squared plus R2 squared, which I chose as 11.25, minus 2 times 15 times 11.25 times the cosine of alpha. Now alpha is this angle between R1 and R2, right? But I don't have that. What I have is on here is theta 2 is the distance from my x1 around to R2. Okay, so this is what's being measured by theta 2. But we know the angle of a straight line is 180 degrees. So what I need to plug in is 180 degrees minus theta 2, which I set at 105. So I plug in 180 minus 105. And you want to check, make sure your calculator is in degrees and not radians. Mine is. So we plug that in, and I get this distance is 16.25457 blah 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 centimeters. Okay. So now let's rip up this robot arm. So I am going to circle the placement of my end effector, just so that I don't get it mixed up with all my other dots. So what I want to do now is I'm going to connect from the center of each dot across to the center of the opposite dot. Okay, so I've got x sub 0, y sub 0. So x naught, y naught. And then do the same thing here. Connect those dots. Connect those dots. So I've got x1, y1. And as you can see, we've got x1, y1, this origin, we'll call it O1, this is O naught. The distance from O naught to O1 is going to be 15 centimeters. We can verify that. Should be 15 centimeters. Now what I want to do is I want to verify that the distance from the center of this origin to this point, it's not going to be exactly 16.25457. My ruler won't measure to that accurate. There's also going to be user error, because I'm not standing directly above these, so I can't tell. But this is it's close. It's about 16.25 centimeters. So that's one thing that you can do with this robot arm. Okay, so another thing that we can do with this robot arm, I have limited theta 1 between 330 degrees and 105 degrees, and I've limited theta 2 between 330 degrees and 120 degrees. Now, these limitations I picked simply so that I could fit everything that is going to happen in the camera frame. You can choose whatever limitations you want, or have no limitations. Now, theta 1 is always going to be limited, as I discussed earlier. But what we can do with this is we can actually sweep out, and I'm just going to use 15 centimeters as the tip of my end effector, but we can actually sweep out and draw our workspace with this robot. So we can get a much better representation of what our workspace would actually look like. Now, hopefully, as time goes on, it'll be easier and easier for these arms to move. The rivets are still pretty stiff in this particular arm, but as you can see, you can get kind of a general shape of what the workspace is going to look like for this setup of this robot. You know, it'd be this whole region that's swept out. You know, the end effector can be any place inside of this line. Obviously, that's going to change based on how you limit theta 1 and theta 2. For these particular limits, this is going to be the space that our end effector can reach.